Right now, old measurements from a small stretch of California's San Andreas Fault are revealing dozens of movements that produced no felt shaking at all. They lasted only hours. No sirens, no cracked dishes, no dramatic line on a local seismograph that would make anyone stop what they were doing. Researchers found them by training a deep learning system to comb through years of exceptionally sensitive underground measurements near Parkfield. The result is not an alarm for California, and it is definitely not a timetable for a huge earthquake. It is stranger than that. A fault section scientists have watched for decades was apparently making short, quiet adjustments that conventional searches had not fully recognized. Imagine standing on a ranch above that fault. Your coffee stays level, a fence post does not rattle, yet far below, rock is shifting in the same sideways direction the fault has been accommodating for ages. That is real motion, just on a pace too slow to launch the waves we feel as an earthquake. One question is hanging over the whole discovery. When a fault releases a little stress silently, does it settle its neighborhood down, or does it rearrange the pressure around it? The answer begins at Parkfield. So why did scientists choose this particular stretch of fault as their underground listening post? Parkfield is a tiny community in Central California, but geologists treat the ground beneath it like a major field laboratory. The town sits on the San Andreas Fault system, the enormous boundary where the Pacific Plate and the North American Plate slide past one another. This is not a crack that opens like a zipper. The plates mostly travel sideways, inching along in a right lateral direction. Stand on one side and look across. Over geologic time, the far side is headed northwest. The whole fault system runs roughly 800 miles through California. It crosses very different landscapes and, more importantly, very different mechanical neighborhoods. Some portions remain strongly locked for long intervals. Others creep, meaning they accommodate part of the plate motion through smaller, steadier movement. Parkfield lies near a transition zone where that contrast is especially useful to study. You may know the San Andreas through images of a single giant future rupture. That image catches only part of the story. A fault is not one clean seam with one mood. It is a complicated zone of broken rock, fluids, bends, rough patches, and changes in temperature and pressure. One section can slide gradually, while another nearby section resists movement. Nature did not build this thing with a control panel marked quiet and earthquake. The long-term rate of plate motion is only a few centimeters each year. Close to the speed fingernails grow, slow, almost absurdly slow, yet the distance accumulates. Where a fault patch sticks, the surrounding crust can deform as the plates keep trying to pass. When a stuck patch finally ruptures quickly, energy becomes seismic waves, and those waves are what turn a geological process into a human emergency. California's history makes that distinction impossible to ignore. The 1906 San Francisco earthquake ruptured a long northern section of the San Andreas and was followed by devastating fires. The 1989 Loma Prieta earthquake, on a related part of the broader fault system, showed how a powerful quake can disrupt roads, bridges, homes, and daily life in seconds. Neither event tells us a large earthquake is imminent today. They explain why scientists care so much about the physics of stress and slip. Parkfield has been instrumented for a practical reason. It offers a chance to watch a fault at close range before, during, and after small and moderate changes. Networks there include seismic stations, GPS instruments, creepmeters, and borehole strainmeters. Think of them as different senses. One listens for shaking. Another tracks positions over longer periods. Another notices a fault's shallow creep. Another feels minute changes in how the crust stretches or squeezes. For years, those instruments supplied an extraordinary archive. The surprise was that some of its quietest signals had been hiding inside it. What kind of fault movement can stay in plain sight without producing the shaking everyone expects? An ordinary earthquake is fast. A patch of fault suddenly slips, the surrounding rock jolts, and elastic energy races outward as seismic waves. Depending on the size and distance, you might feel a wobble, a sharp kick, or a long rolling motion. Instruments detect it quickly because the ground itself is vibrating. A slow slip event operates on a different clock. Instead of rupturing in seconds, the fault moves gradually over hours, days, or sometimes longer. That slower pace means it can release deformation without creating the strong, high-frequency shaking people associate with an earthquake. Scientists sometimes call these silent earthquakes, but the phrase can mislead. The fault is not doing nothing. It is simply moving in a way that does not make a noticeable seismic racket. In the new Parkfield research, the team looked for short-duration, slow-slip events in continuous borehole strain data. These sensors do not wait for an earthquake wave to arrive. They record tiny changes in the shape of the surrounding crust. If rock around the instrument becomes ever so slightly more compressed or stretched, the sensor can register that change. The signals are subtle, and they are mixed with many other influences, which is why finding them is difficult. The researchers used a deep learning workflow to identify recurring patterns in those long records. Rather than handing the computer one perfect template and telling it to find copies, they let the method learn compact representations of daily strain patterns and group similar behavior. That matters. Slow slip signals do not always arrive as identical, tidy shapes. Real data is rude. It contains weather effects, instrument quirks, long-term trends, and all the awkward variations the planet contributes for free. The analysis produced a catalog of dozens of previously unrecognized short events near Parkfield. Each one appears to have released strain over only a few hours. Nearby creepmeters provided independent support for many of the candidates, giving the team a separate line of evidence that the patterns were not merely a computer sorting noise into attractive clusters. That is the central claim, and it is worth stating plainly. The study does not say the San Andreas suddenly began behaving in an entirely new way this year. Slow slip has been observed in many tectonic settings, and Parkfield has long been a target for studying complex fault behavior. What changed is the resolution of the view. Researchers have a stronger way to locate a class of brief, shallow events that were difficult to extract from continuous measurements. You can picture it as changing from a blurry night photograph to one with sharper focus. The scene is not necessarily new. Details that were always there become separable from the dark background. But if those signals were sitting inside the record, why did conventional searches miss them? The answer begins with the scale and clutter of the measurements. The first obstacle is scale. A fault can extend across a state, while the deformation that announces one short, slow slip event may be tiny at a single instrument. Your body is built to notice a sudden loss of balance, not a minute change in the dimensions of the crust beneath you. Even a very good human observer would have nothing to look for on the surface. The second obstacle is time. Fast earthquakes create a distinct burst. Slow deformation blends into the background. Picture trying to notice the hour hand of a clock move while someone keeps nudging the table, changing the room temperature, and opening and closing a nearby door. The hand is moving. The problem is that almost everything around it is moving too, and much of that extra motion is larger than the detail you care about. That is close to the strain meter problem. The instruments are extraordinarily sensitive, but sensitivity does not equal instant clarity. Tides add small loads to the crust. Rainfall and groundwater can alter local strain. Temperature shifts affect instruments and rock. Long-term tectonic deformation continues underneath it all. Then there are gaps, maintenance periods, and the ordinary mess of a real observing network. A meaningful event is one thread in a densely woven fabric. Consider a long musical recording with a quiet triangle struck somewhere behind an orchestra. The triangle is present. A listener could miss it because the rest of the sound is louder, not because the triangle failed to ring. Now make the orchestra play for years, add static, and ask someone to identify every triangle note without knowing exactly when it should occur. That is the level of patience traditional inspection can demand. You might wonder why the team did not simply lower the detection threshold. Because doing that would also capture more false positives. A weak signal might be a slow slip event, a rain-related response, an electronic disturbance, or a combination of ordinary effects. Scientists need a method that is sensitive enough to find small events, yet disciplined enough not to promote every wiggle into a discovery. The difference matters because a dramatic claim based on bad classification is worse than no claim at all. The Parkfield result is useful only if the newly recognized patterns hold up against other measurements and physical checks. That is why the machine learning component is not the whole story. It is the beginning of a filtering process that must survive skeptical testing. What could a learning system separate from that clutter, and how could humans test its answer? That is the mechanism of the investigation. At the foundation is a simple geological fact. The plates do not stop trying to move because a small section of their boundary happens to be stuck. Motion is continually supplied by forces acting across a vast region. The local result depends on friction, rock properties, the geometry of the fault, pressure and fluids within fractures, and the temperature and pressure conditions at depth. Change those ingredients, and the same overall plate boundary can behave very differently from one patch to the next. A fully locked patch stores elastic strain in nearby rock. A creeping patch lets some of the relative motion occur gradually. Between those end members are many intermediate behaviors. Short, slow slip events belong in that middle territory. They are not fast ruptures, but neither are they perfectly steady creep. They are transient adjustments. The fault slips more rapidly than its background pace for a limited period, then returns toward its prior behavior. At Parkfield, borehole strain meters provide the raw material for spotting those adjustments. The instruments sit below the most distracting surface conditions and track extremely small changes in strain. Their record is continuous, which is both their superpower and their burden. A few dramatic events would be simple to inspect. Years of subtle data produce an ocean of possibilities. The researchers prepared the records so the model could compare patterns in time and frequency. They then used an autoencoder, a form of neural network designed to compress complicated input into a smaller internal description and reconstruct it. If that sounds abstract, imagine reducing a stack of cluttered sketches into a few traits: where the lines rise, how long the curve lasts, whether the shape is smooth, and how it differs from background variation. Similar daily patterns land near one another in that reduced space. After that, unsupervised clustering helps separate groups of days that share distinctive features. The point is not that the machine knows geology in the human sense. It does not stare through the earth. It is a very persistent pattern sorter. It can compare a huge number of records without losing concentration after the 500th nearly identical day. That makes it well suited to signals researchers expect may be faint, variable, and buried in a very large archive. The candidate events still require geophysical interpretation. The team examined their timing, spatial consistency, and relationship to nearby measurements. Creepmeters, which track shallow relative motion across a fault, offered an independent check for many events. The estimated slip direction also matched the known right lateral motion of the San Andreas. That agreement does not eliminate every uncertainty, but it raises the result well above a software-generated curiosity. There is another important detail. The events were inferred to be shallow and short-lived. They are not a claim that a giant locked section suddenly slid unnoticed. The inferred behavior concerns a particular monitored environment near Parkfield. You should resist the temptation to stretch a local catalog into a statewide verdict. Faults are regional systems, but their details are stubbornly local. Once the catalog existed, researchers could finally ask whether quiet slip was followed by another subtle fault signal, and that comparison supplies the study's sharpest turn. That second signal is called a low-frequency earthquake, often shortened to LFE. These are very small seismic events with energy concentrated at lower frequencies than typical earthquakes. They are not the sort of thing you feel in your kitchen. They are detected by sensitive instruments and are often associated with slow fault processes at depth. When the Parkfield team compared the timing of their short, slow-slip catalog with low-frequency earthquake activity, they found a systematic increase in LFE activity after slow-slip events. That is the most attention-grabbing part of the study because it suggests the quiet surface near deformation was not isolated. It was statistically linked to changes in seismic behavior nearby. The careful word is linked. The work does not demonstrate that every slow-slip event directly causes every later LFE, and it does not identify a single universal mechanism that applies to all faults. In a complex fault zone, two processes can respond to shared conditions, or a slow event can shift stress in a way that makes another process more likely. Sorting those possibilities out will require more observations and more models. Still, the physical idea is reasonable. Slip changes stress. If one part of a fault moves, however gently, the forces around it do not remain frozen in place. Some nearby patches may experience a slight reduction in stress. Others may receive a small increase depending on their position and orientation. Think of a crowded bookshelf. Remove one book carefully and the books beside it settle by a millimeter. Nothing crashes, but the arrangement changes. For a fault near a threshold, a small stress change can matter. It might encourage a weak patch to slip, or it might make another patch more stable. The direction and magnitude depend on the actual geometry and conditions, which is why scientists do not translate this result into a simple slogan such as "silent slip is good" or "silent slip is bad." Both statements would be too blunt for the evidence. The study strengthens a broader view of earthquake physics. Faults do not only alternate between complete stillness and destructive rupture. They can release strain through steady creep, brief, slow-slip episodes, low-frequency earthquakes, tremor, ordinary microearthquakes, and larger seismic events. Those behaviors are different, but they may be connected through the same evolving stress field. That continuum is scientifically powerful because it gives researchers more things to measure. A damaging earthquake may be rare at one location. Subtle deformation and tiny seismic signals can occur far more often. If those smaller signals encode useful information about fault conditions, they may help refine physical models long before anyone can make precise forecasts. This is where the story can drift into alarm if we are careless. A connection between slow slip and LFEs is not a countdown clock, and the research does not say Parkfield has sent a warning to Los Angeles, San Francisco, or anywhere else. The more honest turn is less cinematic, but more valuable. The fault is giving off more kinds of information than researchers previously knew how to read. What happens when a discovery changes the model but does not justify a warning? The objections matter because they determine how far this result can honestly travel. First, machine learning is not a substitute for scientific judgment. A neural network can surface patterns, but a pattern is not automatically a physical event. Detection thresholds, instrument artifacts, incomplete records, pre-processing choices, and the way clusters are defined can all shape a catalog. The Parkfield researchers addressed that problem with independent creepmeter support and consistency checks, but follow-up work is still essential. Second, correlation has a notorious habit of sounding more decisive than it is. If LFEs rise after a set of slow slip events, the timing is meaningful. It tells researchers that the processes are not behaving like unrelated dice rolls. Yet timing alone does not prove the exact stress pathway. A deeper driver could influence both. Different parts of the fault could respond with different delays. The observed association is a clue, not the final blueprint. Third, Parkfield is not a miniature version of every dangerous fault segment in California. It is a heavily monitored transition area with its own structure and history. The southern San Andreas, the northern San Andreas, offshore faults, and subduction zones each have distinct conditions. A method that succeeds at Parkfield may need different training, different instruments, or different interpretation elsewhere. You should also keep the word slow in perspective. A slow slip event may release some local strain, but that does not mean it drains every form of stored stress from an entire fault system. Nor does it mean the next large earthquake must follow. Some slow slip regions host recurring events without producing major ruptures nearby. In other tectonic settings, slow phenomena have occurred around significant earthquakes. Nature is refusing to give us a one-line rule. The biggest pushback concerns prediction. Earthquake early warning and earthquake prediction are not the same task. Early warning begins after an earthquake has already started, when instruments detect the first waves and send an alert ahead of stronger shaking that may arrive later. Prediction would mean reliably specifying the place, time, and size of a future earthquake before it begins. Modern science cannot do that for San Andreas earthquakes, and this study does not claim otherwise. That distinction is especially important for you as a viewer because alarming language spreads faster than careful language. The fault moved quietly can be true. A giant quake is about to happen does not follow from it. The responsible response is not panic and not dismissal. It is to understand what was actually observed and to use established preparedness guidance for any earthquake-prone region. There is one more challenge. Discovering more events can initially make a fault seem more mysterious, not less. A larger catalog reveals variation in size, duration, and timing that earlier models smoothed away. That can feel like stepping backward. In science, it is often the opposite. Better questions arrive after the easy assumptions fail. So if this finding cannot forecast the next earthquake, what has it genuinely delivered? The answer is more concrete than a scary headline and more useful than one. The firmest achievement is observational. Researchers built a workflow that found a previously undercounted population of short, shallow, slow slip events in continuous Parkfield strain records. That alone is a meaningful advance. A process that had been difficult to see can now be cataloged, compared, and tested. The second achievement is validation. Nearby creepmeters supported many of the inferred events, and the inferred movement was consistent with the known sideways sense of motion on the San Andreas. Independent agreement is crucial. It means the study does not rest on a model's confidence score or on a single sensor doing something peculiar. The third achievement is the statistical relationship with low-frequency earthquakes. The study reports that LFE activity increases after the short, slow slip events. That gives researchers a measurable target for future work. They can test whether the relationship appears in different time periods, with other instrument arrays at other locations, and in physics-based simulations. For you, the practical lesson is almost counterintuitive. The payoff is not a new consumer warning app that tells you to leave town because a hidden event occurred. It is a better map of the behavior already happening inside an active fault zone. Better maps are how hazard science improves over time. First observe, then repeat, then model, then test whether those models improve decisions. There is a quieter win as well. The study shows that valuable discoveries may be sitting inside records scientists already collected. Building a new instrument network is expensive and takes years. Re-examining high-quality archived data with methods designed for subtle patterns can extend the value of work that field teams have maintained for decades. Old data is not old news when the questions get sharper. That does not make artificial intelligence a magical answer. It makes it another scientific instrument, one that has to be calibrated against reality. Used that way, it can help researchers spend their attention where it matters most, on patterns that deserve physical explanation rather than on endless raw plots. There is also a lesson here about confirmation. The strongest discoveries are rarely a single dramatic readout. They are a chain. An unusual pattern appears, another instrument supports it, the direction of motion makes geological sense, and the timing matches a second process closely enough to justify further testing. Each link narrows the chance that the result is an artifact. None turns uncertainty into certainty, but together they make the observation worth building on. You can think of the catalog as a new set of entries in a field notebook, not a final verdict stamped in red ink. The Parkfield catalog is therefore not the conclusion of a fault mystery. It is a starting point that raises one practical question. What should scientists do with this new catalog next? The immediate next step is replication. Researchers will want to apply related detection methods to other intervals of Parkfield data, other stations around the fault, and other types of geodetic measurements. A result becomes more persuasive when a different team, a different pipeline, or a different instrument network arrives at compatible conclusions. One promising direction is combining several data streams rather than asking any single sensor to carry the argument. Strainmeters record tiny deformation. Creepmeters capture shallow motion across the fault. GPS networks trace position changes over longer spans. Seismic arrays detect low-frequency earthquakes, tremor, and ordinary micro-earthquakes. Satellite radar can measure broad ground deformation in some settings. Each has blind spots. Together, they can make a richer picture. Imagine watching a stage play from behind a curtain. One narrow gap lets you see a hand, another lets you hear footsteps. A third reveals a change in lighting. None alone gives you the whole scene, yet the combination tells you far more than any single glimpse. Fault monitoring works the same way. The Earth rarely delivers a fully labeled signal. Scientists reconstruct behavior from partial observations. Machine learning may become especially useful as these records grow. Modern networks produce more data than a human team can inspect line by line. The best systems will not merely flag unusual shapes. They will report uncertainty, identify which instruments supported a candidate, and make it possible for analysts to audit why the model drew its conclusion. A black box that cannot be checked is a poor fit for high-stakes science. There is also a question of transferability. Parkfield has an unusually dense history of measurements. Many faults worldwide do not have the same coverage. If researchers hope to search for similar short events elsewhere, they must learn what minimum data quality and sensor spacing are required. Some places may reveal rich catalogs quickly, others may only yield ambiguous hints. Absence of detection would not always mean absence of slow slip. Another frontier is physical modeling. Once scientists have more event timings, durations, estimated sizes, and locations, they can compare them with friction models and stress transfer calculations. Do certain small events cluster after rainfall, tidal loading, distant earthquakes, or gradual changes in creep rate? Do low-frequency earthquakes consistently follow in the same part of the fault? Do some events coincide with changes that appear in GPS or satellite data? These are testable questions, not promises of prediction. The broader competition is not between humans and algorithms. It is between two ways of treating a difficult dataset. One way assumes that only the biggest, easiest signals deserve attention. The other accepts that subtle motions may be physically meaningful if they are found rigorously and checked independently. Parkfield is giving the second approach a real trial. What should you watch for in the next few years? Look for peer-reviewed replications, applications at other faults, improved multi-instrument catalogs, and careful tests that distinguish association from causation. Be wary of anyone who turns a new detection technique into a claim that the next major earthquake has been scheduled. That leap is not science. The deeper story is that a supposedly solid landscape is active on more timescales than human intuition likes to admit. We notice a fault when it makes a violent move. Researchers are learning to notice it when it whispers, too. That brings us back to the small number in this story that seems almost laughably slow. Global style lock. Append this to every prompt. Traditional documentary oil painting on canvas, painterly realism, thick impasto and palette knife texture, tactile layered brushwork, restrained palette of ochre, umber, charcoal, dusty sage, deep Prussian blue, and sparse electric cobalt instrument glow. Dramatic but scientifically grounded cinematic lighting. Detailed natural landscapes and rock textures, 16:9 landscape frame. No readable text, no captions, no logos, no watermark, no UI overlays, no photorealism, no CGI, no cartoon style. Recurring character lock. Whenever a human field scientist appears, show the same fictional lead geophysicist, Dr. Mara Reyes, a 38-year-old Latina woman with warm olive brown skin, deep brown eyes, a narrow oval face, dark black hair in one low braid, a weathered slate blue field jacket over a cream Henley, khaki field trousers, scuffed brown hiking boots, and a small leather notebook. Her manner is calm, observant, and practical. Keep this exact identity, outfit palette, and silhouette consistent across all prompts where she appears. Do not introduce another recurring scientist as a substitute for Mara.